How long is I? Well, I can tell you for starters, the number 1, that's 1 long. The number 2, well, that's got a length of 2. I reckon the number -1 also has a length of 1. So surely the number I, which is sitting right there, I reckon that's got a length of 1 as well. Complex numbers are vectors, which means that they've got lengths. So the number I is 1 long, and then a number out here, like 1 plus I, probably a little bit longer than 1. I reckon that line's just a bit longer because it goes diagonal. So in general, because complex numbers are vectors, and vectors have a length, complex numbers have a length. And it's the same formula. So you take the real bit squared and you add on the imaginary bit squared. That's literally all you do. So let's take this number like 3 plus 4i. I could graph it here. Here's 3, here's 4. Bam. That's a line. And that line has a particular length. Turns out that length is 5. We'll see why in a second. So if I want to do 3 plus 4i, and I call this z for complex number, then mod z equals square root of 3 squared plus 4 squared, which is square root of 9 plus 16, which is root 25, which is 5. Beautiful stuff. You can also work this out just using plain old Pythagoras. That length there is 3. That length there is 4. We've got a right angled triangle, and if you label this as sort of like a, b, and c, then c squared equals a squared plus b squared. Or in other words, c squared equals 3 squared plus 4 squared. And essentially c squared equals 25, so c equals 5. The length formula is literally just Pythagoras in disguise. So we'll do a couple more examples. Mod z of this one, 3 plus 2i. Mod z equals a square root of 3 squared plus 2 squared, which is going to be square root of 9 plus 4, which is square root of 13. That's a nasty number, so we'll leave it at square root of 13. Mod z for this next one is going to be square root of 3 squared plus minus 2 squared, which is square root of 9 plus 4, which is square root of 13. This one is going to be square root of minus 3 squared plus minus 2 squared, which is square root of 9 plus 4, which is square root of 13 again. Interesting. So what do these numbers have in common? Well, they're basically the same thing. They're just pointing other ways. So if we take another Argand diagram, we plot all those out. That first number that I looked at, 3 and 4i, is sort of going to be, 3 and 2i, is sort of going to be pointing up there. It's got that length. The next one I looked at was 3 take 2i, which is sort of pointing down there. I'm hoping you can agree those two lines, they have the same length. Last one was minus 3 take 2i, which is down there. All these have the same length. That length in all cases is root 13. Root 13 is somewhere in between like 3 and 4. 3 point something. But that's the idea behind length of complex numbers. It works pretty much the same as vectors do. We'll get down into the nitty gritty of all these linked identities, but most of them are fairly straightforward. Like if you times two complex numbers, then their links will times together as well, for example.